All right, well, it's an absolute pleasure to be here today. Today what I really want to do is talk about a subject that is fairly topical at the moment, to say the least. In fact, I think you probably can't go a day without reading something in the newspapers about capturing CO2 and the carbon tax. And I think a little bit later after this lecture, I'd actually be really interested to know what you guys think about the carbon tax, and in fact whether you're anywhere near as confused as I am about it. But what I really want to do today, rather than talking about politics and all of the emotion and the believers and the disbelievers behind global warming and CO2 capture, I want to talk about the science of capturing CO2. And in particular, I think by the end of the lecture, what I hope I've shown you is that, in fact, by understanding the science and the chemistry behind capturing CO2, perhaps we can understand a little better why all of this emotion and concern and problem has arisen over this very topical issue. So I guess where I want to start here is really by recognising that, first and foremost, CO2 is absolutely essential to life on the face of this planet. Without it, we simply wouldn't exist. And you should all be very familiar with this equation for respiration because it gives us life. So, of course, we take in oxygen and breathe out carbon dioxide, and that's where we get our energy from in order to do everything that we do in our everyday lives, like being here and having a great time over the next 2 weeks. But as well as that, plants take in the carbon dioxide that we breathe out, and combining that with water and the energy from the sun, plants make oxygen, which basically revolves around the cycle. And I guess what's key here is that CO2, or the carbon in CO2, isn't always in that format. In fact, carbon is always on the move. So you might also be familiar with the concept of carbon moving through the atmosphere. So what the carbon dioxide that we expel, of course, is taken up by the atmosphere. It is taken up then by plants in this process of photosynthesis. And I guess what you'll notice here, if you just take a look at the carbon flux, and this is actually recorded here in gigatons of CO2, for respiration and photosynthesis, it's about a balance in terms of the flux out and the flux in. Of course, it's not just humans and plants that respire. The ocean also undergoes respiration and photosynthesis. So, of course, algae and marine organisms also expel and take up carbon. And I guess what you'll also notice is there's a huge amount of carbon that's actually locked up in sedimentary rocks. And of course, you'll be very familiar with carbon in fossil fuels. So this is things like coal, oil, and natural gas. But I guess if I can just go back here a moment, what isn't natural about this cycle is the carbon from the burning of fossil fuels. And I guess most recently, you'd be fairly familiar with the fact that we've obviously had a lot of volcanic activity in the world, and that, of course, would have also been contributing to the amount of atmospheric carbon dioxide. But I guess what's really key here is that while for thousands and thousands of years the carbon flux has been fairly constant at about 300 gigatons of carbon per year, that's the natural carbon flux. What isn't natural is the contribution from human beings, from us. So that amounts to about 6 gigatons per year of carbon dioxide. Now, mind you, this is a very small amount of the total carbon flux, only about 2%. So I guess one of the arguments here against the contribution of humans to global warming is the fact that, sure, this is a really small % contribution to the total carbon flux. But it's not natural because not only is this increasing, ever increasing, it's also adding into this very delicate carbon cycle that maintains life on the face of this planet. And so what's not natural is the fact that fossil fuels are not naturally a part of the cycle. So every tonne that goes into the atmosphere is taken up forever in that cycle of carbon. Now, I guess if you go back to about 2006, when you guys would have been perhaps in the latter years of your primary school or the start of high school, you might have watched this fairly topical film at the time by Al Gore called An Inconvenient Truth. You see the little penguins here walking on the sand. But what Al Gore really did was to bring to life just how important this rise in CO2 concentrations had been. In fact, in the post-industrial era, the amount of CO2 is what Al Gore said contributed to an increase in the amount of CO2 in the atmosphere from 300 ppm to 388 parts per million. And that's the current day estimate for the amount of CO2 in our atmosphere. Now, the upshot of all of this is, as Al Gore pointed out, that for 400,000 years before the present day, there has been a cycle of temperature. So the Earth has warmed and the Earth has cooled. And this basically has come from ice core measurements from the Antarctic. So these measurements go back way, way, way into the hundreds of thousands of years before the present day. Now, what isn't natural about this is this bit of a spike here over the last 20 years. So this is the post-industrial era. And basically here, the concentration of CO2 in the atmosphere has risen by about 100 ppm, and it's ever increasing. So it's true that, yes, the Earth has cooled and warmed over thousands and thousands of years. What isn't natural is the fact that most recently there has been a huge spike in the amount of CO2 in the atmosphere, and ice core measurements from ice cores show that this is really causing a warming of our Earth. So anywhere up to 2 to 3 degrees over the last 100 years. Now, why is this so? Well, you're probably familiar with, I guess, the argument that, well, it's due to fossil fuels. And I guess if you have a look at what the world's most dominant energy sources are, then you'll see worldwide that, in fact, it's oil that is used most predominantly around the world for energy. Now, I wanted to show you the Australian story here because, for us, the story is quite different to the worldwide story. So I should just point out that coal is actually the most carbon-intense fuel of all of these types of fuels. Here's the Australian story. In Australia, we have huge reserves of black and brown coal. In fact, we have larger reserves of brown coal than black coal, but brown coal actually has a very, very high water content. And what that means is that it's not great for energy production. So in Australia, most of our energy production is actually from black coal, which is what you see here. You'll see there's a little bit from renewables, none from nuclear, though we do have a nuclear reactor basically in our backyard. That's at Lucas Heights, and I guess you'll see worldwide there is quite a substantial amount of nuclear energy used, but with recent events, who knows what the long-term prospects of nuclear energy are going to be. So here's a little bit of a snapshot of the world taken by a spaceship. And what you can see here is basically the world's major energy consumers. So you can pretty easily pick out North America there and Europe, a little bit here in Australia. Now, the upshot of all of this energy usage is that carbon dioxide from fossil fuel combustion is really the major contributor to greenhouse gas emissions. And you can basically see that, in fact, it's fossil fuel combustion mainly for electricity use, a little bit less for transportation, so mainly for electricity, is basically the major contributor to greenhouse gases. So I should point out, water is actually also a greenhouse gas, so you should just keep that in the back of your mind. Water's not as benign as you might think. Okay, but of course, methane is also another major greenhouse gas, emitted actually mainly by cows, as well as nitrous oxide. You might remember back to the late 80s, I guess this is when you guys were not too long after you were born, but the world had a major crisis in CFCs, so these are from aerosol cans. In fact, the world surmounted that problem very well, and I hope that with CO2 we can likewise surmount the problem. But what is most interesting here, and in fact perhaps alarming, is that if we look into the future, say 20 years into the future, then what you'll notice is that for developing countries, the energy demand is only projected to increase. Now, for each consumer in a developing country, the total energy usage would be less than for a person in a developed country. But just think about the population expansion, particularly in India and China, so these areas here, and overall, with that population explosion, you can see that the projections really do mount to a massive increase in energy demand. Now, I think one thing that might concern you a little bit, as it does me, is that here in Australia, we are actually the world's worst carbon dioxide emitters. In fact, per capita, we emit 4 times the global average. So just keep that in the back of your minds. The reason is, and this all comes back to the fact that coal, which is a very carbon-intense fuel, is our major energy source. So that's the reason why we're the world's worst carbon dioxide emitters. Okay, now another core concept that you probably have heard quite a bit about. This is the greenhouse effect. So this is basically the reason or the explanation for why the Earth is warming with all of these greenhouse gases like CO2 that are being emitted. So, of course, energy from the sun impinges upon the Earth's surface. It's radiated back from the surface, but because you have this sort of a cloud or this atmosphere that is very heavy in greenhouse gases surrounding the Earth, that heat, that energy gets trapped very, very close to the Earth, and as a result, the Earth heats up. So I guess, again, I should say that, remember, CO2 is absolutely essential to our lives, and the greenhouse effect gets a bit of a bad rap. But in fact, if we didn't have the greenhouse effect, our I guess, Earth would be about minus 22 degrees Celsius. So without the greenhouse effect, we couldn't exist. But when the greenhouse effect runs away, the Earth obviously warms up too much. So just keep in mind the fact that CO2 and the greenhouse effect, these aren't always negative terms. There is a very positive explanation for these things. Okay, so what can we do about it? Well, of course, we can switch off our lights sooner. We can switch off our computers when they're not being used, etc., etc. We could also switch to less carbon-intense fuel. So remember I said that coal is an extremely carbon-intense fuel, so we could switch to natural gas. Of course, we could use renewable energies, and I'll talk a bit about that later. But in the short to medium term, what do we do now? And the answer really comes down to one of the major strategies being looked at worldwide, which is carbon capture and storage. And I guess there are lots of drivers for this. So the United Nations has actually set up a huge project here. There's the Intergovernmental Panel on Climate Change. Australia signed the Kyoto Protocol a few years back, and what that means is that by 2020 we have to return to our 1990 levels of emissions. And I put the carbon tax here. I don't understand it. We can talk about it later. Whether that's going to be a driver for CO2 capture and reduction, I don't know. But it is actually interesting that in Norway about 20 years ago, they actually brought in a carbon tax, and it has actually reduced CO2 emissions in Norway. So you can think about that a little later. Okay, so what is CCS, or carbon capture and storage? Well, it basically embodies 3 technologies. So we've got various processes that emit carbon dioxide. Once you have your energy, so that might be electricity or or your product like cement, what happens is the flue stream or the effluent stream from that industry is taken off to another part where the CO2 is separated out of that effluent stream or that flue stream. It's then compressed and it's then taken off and stored somewhere. Okay, so we'll talk about each of these different parts as we go along. Okay, so Australia's largest power plant, this is a coal-fired power plant, is actually just north of here, not too far. It's up in the Hunter Valley. And you'll see that it's about half the size of the world's largest power plant, which is in Taiwan. And basically, just to give you a bit of a snapshot of what's actually going on in a coal-fired power plant, you can see that basically the coal is combusted, and that combustion then turns a turbine, which gives us electricity. So the other thing you should note is that no Australian power plant currently captures any CO2. Everything is emitted. Okay. So how much CO2 is emitted? Well, if you take this Olympic swimming pool just here, and this is just near the Harbour Bridge, as you can see on a beautiful day, then in fact, if you just take one of Australia's smaller power plants, so a 300 megawatt plant, just remember that in fact most power plants in Australia are actually much bigger than 300 megawatts, so this one's about 5 times that size. But from a typical 300 megawatt power plant, then 360 Olympic swimming pool size, trying to think of the right way to say this, the volume of an Olympic swimming pool's worth of CO2 is emitted every day. So this is actually a conservative estimate. You're probably looking at about 1,000 times the volume of a swimming pool emitted every day from each power plant. Now, throughout the whole of Australia, last year, what that really amounts to is about 12 times the entire volume of Sydney Harbour. Okay, so that's just to sort of give you a bit of a picture of how much CO2 we're actually talking about here. Okay, so what can we actually do about it? And here's the real science and the real technology behind CO2 capture. So the idea here of CO2 capture is that after processing in a plant, so this could be a cement plant or a power plant, you basically separate your carbon dioxide from all of the other gases in that effluent stream or that flue stream after you've done the combustion. So I should also point out that up the top here, here's just a little drawing of the actual structure of CO2. Okay, so this is going to become pretty important later on when we talk about some of the chemistry. But basically what you're looking at here is carbon dioxide is basically a carbon atom which is bound doubly to 2 oxygen atoms. And it's a linear molecule. That's actually very important. Okay, so the shape of carbon dioxide is very important. Okay, so let's actually have a look at what you would find in a typical effluent stream from a power plant. This is actually for a coal-fired power plant. So you'll see here that basically most of the effluent stream is actually nitrogen. Okay, so that's pretty benign. Carbon dioxide actually only makes up about 15% of the effluent stream. And you can see there's some other trace elements in here and gases in here as well. Now what's important is that flue gas is actually a pretty low pressure gas. It's only at about 1 atmosphere. Okay, so around about atmospheric pressure. Now here's what actually goes on in CO2 capture. Okay, and I should mention that CO2 capture is actually used for natural processing in a few places around Australia, but not in any coal-fired power plant. Okay, so here's the crux of the argument. This is a bit of an engineering take here on what happens. So you've got 2 important parts to this process. You've got an absorber column here, okay, and you've got a desorber column here. So in the first instance, what happens is our flue gas actually passes into the absorber column, and down the top of the column we have this very fine spray of a water-based solution, which I'll explain in a moment. But basically what happens is the flue gas passes in here, the other water-based solution passes in the top, there's a reaction, a chemical reaction that occurs in this absorber, which we'll talk about in a second. And the carbon dioxide is actually selectively removed from that flue gas. And it then passes out the bottom of the column and into this second column, which is called a desorber column. And in here what happens is the temperature is actually raised. So you can see we have to heat the desorber column up. Remember, this is an aqueous solution that comes out of here. So we're talking temperatures just above the boiling point of water here. And what happens is the carbon dioxide is actually selectively removed. And all of the other components of flue gas have already been removed in the first part of that process. Okay, so once the carbon dioxide comes out here, it's at around about 1 atmosphere, around about atmospheric pressure. Okay, so here's the chemistry, the bit that I really love. Now, believe it or not, the process that I've just described to you was actually patented right back in the 1930s. It's still the same process that is used today, which might be a bit sad, but obviously it's a very important process. Now, industrially worldwide, the most important reagent that is used is what's called methanolamine. So just going back a moment, when I described that there was this other solution coming in the top of the column here that was a water-based solution, that water-based solution contains this particular chemical called methanolamine. Now, it's an amine because it contains a nitrogen group bound to 2 hydrogen atoms here. So the white balls are hydrogen atoms. The blue here is a nitrogen atom. The grey here are carbon atoms. And then it's called an alkanolamine because there's basically an alcohol, an OH group. So the red is an oxygen. The white is a hydrogen dangling off the other end. Okay, now, you might all be familiar with, I guess, the concept of acid-base reactions, which you might have talked about in school. And methanolamine is a base. Okay, it's basic because it has this nitrogen end down here, which is very, very electron rich. Now, CO2, if you think about this, what is CO2 used in? Any ideas? Wonderful, so Coke. Okay, so carbon dioxide is very acidic. Okay, so we've got a basic component here. It's reacting with an acid. What do you think is going to actually form? Wonderful. Okay, I can tell you've all been listening. Okay, so there's a reaction, a very selective reaction between the acid, the acidic carbon dioxide, and the basic methanolamine. Okay, and that's actually key to how carbon capture takes place. Now, it's not just methanolamine that's used industrially. In fact, secondary amines like diethanolamine are also used. So by secondary here, I just mean that the nitrogen here is bound to 2 carbon atoms, but it's only bound to 1 here. So this is a primary amine, this is a secondary amine, and in fact, tertiary amines are also used industrially. So tertiary because here it's bound to 3 carbon atoms. And all of these solutions are about 25 to 30 weight% aqueous solutions. Okay, so here's the real chemistry behind what happens. Methanolamine reacts very selectively with carbon dioxide, and you've just told me it forms a salt, which is basically what you're looking at here. There's a negatively charged anion called a carbamate. So you can see here that the carbon dioxide has actually reacted very selectively with the nitrogen atom of the methanolamine. Now, remember that we've got a carbon atom here with 2 oxygen atoms. The carbon here is a little bit positive compared with the oxygen atoms. The nitrogen atom here has a lot of electron density, so you can see that preferentially it's the electron density on the nitrogen which is attracted to the little bit of positive density on the carbon atom to basically give you this carbamate. Okay, now, I guess what's important here is that at about 40 to 50 degrees, we can form this carbamate in the absorber column. But in order to go backwards in the desorber column, we have to heat this solution up. So remember, we have to heat up that water-based solution to just above the boiling point of water, about 100 to 140 degrees Celsius. Okay, so we've got to put energy in to get the carbon dioxide out. And I'll come back to why that is so important in a second. But I should also mention that industrially, other amines are also used. In fact, this tertiary amine, methyl diethanolamine, is also used. But in fact, the mechanism is very different. So up here, we form a carbamate, but with a tertiary amine, in fact, there's too much bulk or steric crowding around the nitrogen atom, and in fact, it can't form this type of a complex. So instead, you end up with bicarbonate formation. Okay, so I guess what I really want you to take away is that for primary amines, you can form carbamates. For other types of amines, you can form different types of compounds. Okay, but these are reversible reactions. You can get the CO2 back after you've actually done the reaction. All right. Now, this is not meant to scare you. Us chemists have lots of different ways of representing chemical reactions. And what I'm showing you here is exactly what we've just looked at, but I've actually drawn it slightly differently. Okay, so the R groups here are basically just a slightly different representation of what we talked about on the last slide. Now, what I want you to take away from this is the following, and that's that in the case of a primary or secondary amine, we need 2 amines for every 1 carbon dioxide. But for a tertiary amine, we actually only need 1 amine for every carbon dioxide. So now that might seem very trivial, but in fact it's not. It has incredibly important implications because you need a lot more of this. In fact, you need double of it in order to do this reaction. Okay, and there are a lot of problems with this. So it's true that methanolamine reacts very, very fast with carbon dioxide, but you need more of it to do the same thing. Okay, so this is really the reason why industrially there's a lot of problems with this process. The other problem is you've just told me carbon dioxide's acidic, and that's absolutely true. And of course, I mean, you know, they talk about acidic carbon dioxide corroding the enamel on our teeth. In fact, in industry, it does more than that. It actually corrodes the equipment. So, in fact, this whole process has a lot of inherent problems. And I guess Mitsubishi in Japan actually came up with a rather interesting solution, which was, well, it's primary amines have their problems, tertiary amines have their problems. Why not go somewhere in the middle? So this is actually what's called a sterically hindered secondary amine. So it is actually a secondary amine with a little bit of steric bulk around it. It still forms carbamates, but they're a little bit less stable, so you don't need to put as much energy in to go backwards. Okay, so we've just talked about the fact that there are some real problems with capturing CO2. You've got a very, very high volume of flue gas. You've got a low concentration of carbon dioxide. Of course, you can, with post-combustion capture, you can retrofit existing power stations, but the solutions are very corrosive. They're very acidic, so that's a real problem. And in fact, carbon capture and storage increases the costs from a power plant by 25 to 40%. Okay, so that's the bottom line that industry are thinking about. And in fact, the capture phase that I've just talked to you about is actually about 2/3 of that cost. Okay, so you can start to see here why there is such an impediment to capturing CO2. It's expensive. Of course, industry are looking for the cheapest way to get around this problem. Okay, so what are the alternatives here? Well, in fact, down in Victoria at the Hazelwood Power Station, they've actually come up with a rather nifty solution to capturing CO2. So what they actually do is they react their carbon dioxide with the particulate matter from the combustion of coal. So basically these big towers that you see here have these electrostatic precipitators in them. They precipitate out all the solid particulate from the combustion process. That contains a lot of calcium oxide, which is a base. The base reacts with the acid to form limestone. So it's actually quite a nifty little solution that they do that they use at Hazelwood. Now, Hazelwood's quite an interesting place because it's actually the site of the first CO2 capture demonstration project in Australia, and one of the first worldwide. And they're actually looking at 3 different solutions to capturing CO2. So they're looking at alternatives to solvent absorption, which we've just sort of looked at a little bit. They're also looking at what are called membranes for CO2 capture, as well as adsorbents. And this isn't a typo, it is actually adsorbents and not absorbents. And we'll look at the difference between an absorbent and an adsorbent in a second. But why do you think, would cryogenic cooling be good? I mean, air separation is performed using cryogenic cooling. So do you think that cryogenics might be good for actually capturing CO2? Remember, each of the gases... Sorry?
It's easy to make it into ice, carbon dioxide. So
yeah. You're absolutely right. So it is definitely easy to form solid dry ice from carbon dioxide. Remember, we've got a mixture of gases there, and they all have different freezing points. So yeah, that would absolutely be a solution. One of the issues with post-combustion capture is you have such a huge volume of flue gas, and that is actually the impediment to cryogenic cooling, just because you have such a huge volume that you would have to basically put all this energy into compressing all of that CO2. But in fact, cryogenics is being looked at for a different type of capture process, which we'll talk about later. But basically, people are sort of going away from the prospect of cryogenic cooling. Okay, so what would you want in a material that would be good for CO2 capture? Well, you'd want it to be air and water stable. Remember, there's water in a flue stream. Okay? It has to be corrosion resistant, have a high stability, obviously, very high selectivity for CO2, and importantly, if you want it to be reversible, then you don't want to have to put too much energy in to get the CO2 out. Okay, so these are all key requirements for these new types of materials. Okay, so what is the cutting edge here in alternatives to materials for CO2 capture? Well, there are different types of chemical solvents besides the amines we've been talking about, but in general they have a very energy intensive desorption step. You have to put a lot of energy in to get the CO2 out. Remember that I've put the term chemisorption here, and the way these chemical solvents operate is basically there's a chemical bond formed between the solvent and the carbon dioxide. So you often have to put a lot of energy in to break that bond to get the carbon dioxide out again. Aqueous carbonate solutions have been one solution talked about, but again, once you've reacted the carbonate with the CO2, you have to drive the reaction backwards, and this takes a lot of energy. So chemical solvents, there are some prospects there, but there's some real problems with them. One of the very interesting new classes of materials for capture are called physical solvents, and I've sort of separated these two solvents because these ones operate via physisorption. So physisorption is actually a little bit different to chemisorption. Rather than forming a new chemical bond, there's actually just a strong association between the carbon dioxide and the physical solvent. So just to give you a few examples, here's quite an interesting one. Here's an ionic liquid. Now, these things are actually are ions. They're based upon imidazolates. So that's this little group here. These are nitrogen atoms with carbon atoms and hydrogen atoms. Basically what happens here is that the carbon dioxide has a very selective interaction with the positively charged part of the ionic liquid. Now, these ionic liquids are actually incredible solvents. They're liquids at room temperature, but they're ionic. They're benign, they're environmentally friendly, they're green. You can make them in the microwave, believe it or not. So these are one very, very promising class of new materials. But as well as that, there's a lot of other possibilities here. Just remember that you don't form chemical bonds here. You just form a strong association between the carbon dioxide and the actual solvent. Now, the way these work is by a process called pressure swing adsorption. And basically what you do here is you, at very, very high pressure, you force the carbon dioxide and this solvent together, and then when you release that pressure, they, by a flash distillation, they sort of come apart very, very easily. So the amount of energy you need to put in to get the CO2 off is actually very small in this case. Yes?
How long is this option selected?
How long is it selected?
How is it selected? Because this option is not supposed to be selected for what people are.
Well, it's selective in that you have parts of these molecules are highly charged, and that has like an electrostatic interaction between.
That means that even sulfur dioxide is more vulnerable, and all those gases, SOx and NOx, are more vulnerable to be selected.
That's an excellent point, actually. So the point made by this gentleman was that there's also SOx and NOx in a flue stream, and yes, absolutely.
Exactly. In coal, we do have all those, a lot of sulfur impurities.
Absolutely. So that's an excellent point. So in coal, there is a very high amount of sulfur impurity. Actually, what's interesting, in Australian coal, we actually don't do desulfurization because it actually has a very low, black coal has a very low sulfur content. Brown coal has a high sulfur content. But in fact, with black coal, we just use it as is, actually. We don't actually desulfurize prior to the combustion step. But around the world, yes, you're absolutely right. There has to be a desulfurization step prior to carbon dioxide capture. So yes, you need a selective sorbent for sulfur dioxide and SOx and NOx removal prior to carbon dioxide capture. We should talk about that a little bit later as well. Okay, so these physical solvents are excellent candidates for CO2 capture, but via a different mechanism. This has to be high pressure adsorption. Remember that chemical solvents are used as very selective sorbents at relatively low pressures. Okay, so the next really important class of materials for separating CO2 are membranes. And this is, I guess, just one example of sort of how a membrane works. Basically what would happen here is that a flue gas would pass over one side of the membrane. The CO2 is very selectively taken up by the liquid in the membrane, and you've then got the CO2-rich solvent being passed out over the other side. So this is quite an interesting mechanism for gas absorption. And of course, you can make these sorts of things out of all types of materials. So they can be inorganic or organic. You can even make them out of cellulose acetate, which is like a paper-based material. Now, the other way of doing this comes back to this high-pressure option. So if we have flue gas at a very high pressure, we can selectively separate CO2 from the other components of that mixture across a membrane. But remember that flue gas is at a pretty low pressure. It's only at about 1 atmosphere. So in fact, this probably wouldn't work so well for low pressure flue gas separations. But it would work very, very well for some other high pressure CO2 separations that we'll talk about in a little bit. Okay, so we come now to this new class of materials called adsorbents. And as I said, an adsorbent is actually different to an absorbent, like a solvent, because in this case you have this physisorption interaction between the carbon dioxide and the material. So in other words, the carbon dioxide actually adheres to the surface of the material. It's not taken up or absorbed, and no chemical bonds form between the CO2 and the material. And I guess here there's a few interesting classes of these that have been looked at. You'd probably be perhaps very familiar with zeolites. They're actually in everything. I think the largest application of zeolites is laundry detergent, believe it or not. So these things can be either natural or synthetic. And in fact, they have a huge number of different structure types. There's, I think, almost 200 different structure types. This is sort of just one example here. And they're all based upon an aluminosilicate framework. So you can see that basically all of them have these tetrahedral or 4 coordinated silicon and aluminium ions in their makeup. Silicas can also be used as physisorption materials, and I guess the problem with silicas, so these materials contain silicon oxygen bonds, is that they're actually not terribly selective for carbon dioxide. So basically what you have to do is build in some sort of selectivity. So as you might have already realised, in this case you can actually put amines into the materials to make them much more selective for CO2. There's another really interesting class of materials called zips, and I'm going to sort of talk to you a little bit about this in a moment, only because this is basically a class that is sort of on the cutting edge of physisorbents at the moment. And there's another interesting set of materials called MOPs, or metal organic frameworks, that is again right on the cutting edge of physisorbent materials for CO2 capture. Okay, so one thing before we go too much further is remember these materials are porous. Okay, so there's a void space within them. If we go back a second here, you'll notice that, for example, in zeolites, there's actually pores in these materials, and that's sort of the basis of why zeolites crack, are used for petrochemical cracking and so forth. The substrate moves into the material, the catalytic process occurs, and then it moves out of the material. So the porosity is absolutely key here. Okay, so IUPAC, which is the International Union of Pure Applied Chemistry, have just recently come up with this definition for porous materials. And I love the fact that they called this class nanoporous materials, because there's lots of money in nano at the moment. So basically, they define nanoporous as three different size or pore sizes in these porous materials. So you've got microporous materials right down here at the nanometer level. Okay, so we're talking about the diameter of a pore here. Mesoporous materials are a little bit larger pores, so 2 to 50 nanometers, and getting right up into macroporous materials, which are your silicas. Mesoporous materials are usually zeolites. Microporous materials, just going back a sec, are really these two classes down here, the MOPs and the ZIFs. Okay, so as you can see, you can really tune the size of the pore. And what that means is that size does matter. Okay, so basically you can tune the size and the shape of your pore to very selectively, I guess in what's called molecular sieving, to very selectively select the size of the gas particle that you separate. Okay, now there are a number of other mechanisms that are operative here. It's not just that size matters. There are also thermodynamic effects, so you can have preferential interactions. And for example, if we build in a polar constituent to the surface, say an oxygen atom here or there, then the carbon dioxide will have a very strong interaction with that. Remember, CO2 is actually quite sticky, okay, in a sense, likes like. So there's going to be a very strong interaction between two polar parts of, say, the CO2 molecule and a surface. There's also other effects that are operative. So you have differences in the diffusion rates of different gases through a porous material, and getting right down here into basically hydrogen and deuterium are quantum sieving effects. But here's what's important when we're thinking about how would we make a material that is very selective for CO2 capture. So if we think about what our flue stream is actually made up of, then you'll see that in fact CO2, remember, is just a very small percentage of that flue stream. Most of the flue stream is actually nitrogen. Okay, and if you look at this, I guess this is sort of a measure of the size of a gas molecule. You'll notice that, in fact, all of the gas molecules have very different diameters. Remember that the kinetic diameter it's just a measure. It's assuming that the gas is just a spherical ball. But in any case, it is a good measure of the size of a molecule. But as well as that, the polarity of these gas molecules is very, very different. So carbon dioxide is much, much more polar, for example, than nitrogen. So we can use that polarity difference as a way to build in selectivity for carbon dioxide. And that's why that amine-based solvent absorption process is so good for CO2 capture, the nitrogen can just pass straight through because it's not polar, it doesn't react with the amine. Okay, so in terms of how to actually do the separation with the physisorbent material, I mentioned a little earlier this pressure swing adsorption approach. And basically what happens here is we pass a very, very high pressure stream containing carbon dioxide through our powdered material. So here you might have say a packed bed of your adsorbent. The physisorbent selectively adsorbs the CO2, and basically what you do then is you decrease the pressure, or you can increase the temperature, but if we just talk about decreasing the pressure, and as soon as we do that, there's like this flash distillation, and the carbon dioxide is very easily removed. So this whole process of pressure swing adsorption is very low energy compared with that chemical absorption method that we talked about earlier.
I didn't really get the factor which selectively absorbs it. What makes it selective for CO2?
Yeah, so we could think about, remember earlier we talked about the fact that in a porous material there may be parts of that surface that are quite polar and the carbon dioxide interacts very well with that surface. There might be an electrostatic interaction.
So you get the same problem with SO2 and H2.
That's exactly right, but the idea would be that you could do that sulfur,
and
that SOx or NOx removal. Sorry?
Carbon monoxide, even that kind?
There's actually not a lot of carbon monoxide in flue gas. In natural gas sweetening there is, which we'll talk about in a minute, but in flue gas there's actually not a lot of carbon monoxide. But you're exactly right, there are other constituents of flue gas that you have to make sure they're not going to be competitive with this process of CO2 removal. So you're absolutely right in that respect.
And all these is with respect to coal alone.
Sorry?
This flue gas is with respect to coal alone.
I'm sorry, I didn't.
Coal alone.
Coal alone? The figures that I've shown you are actually black coal. Brown coal is a little different. Brown coal has a very high sulphur content and water content. So in Australia we predominantly use black coal at the moment. We don't use so much brown coal, but
the separation process is aimed at separating flue gas from black coal.
yeah, so I'm talking about black coal now. I'm actually going to talk about natural gas in a little bit. And that's the emerging energy of the future, I think. So we'll talk about that in a minute. But this is basically centred around capture from coal, predominantly. Okay, so as has been pointed out, you have to remove other gases from that flue mixture. So you can do a preliminary SOx and NOx removal as well as a preliminary water removal as well. So you could have physisorbent materials in here that were selective for each of these prior to your CO2 removal. So you can see that you really can tune things very, very well with these physisorbent materials. Okay, so here's a topic close to my heart. This is really the cutting edge in physisorbent materials at the moment. These things are called metal organic frameworks, and they're basically they're microporous materials, so they have very small pore sizes up to about, say, 10 nanometres. But what is really key here is that these things have incredibly high surface areas. Okay, so if we just took, for example, a teaspoon of one of the best materials that we had at the moment, then it would actually have a surface area around about the size of an Aussie rules football field. So these things are incredibly adsorbent. They have a very, very high surface area. They have a low density, obviously, because there's a lot of porous space within them. They can have channels connected in 1, 2 or 3 dimensions. And I guess for me as a chemist, what I love is that we can use chemistry to actually functionalise or graft molecules onto the interior surfaces of these things. Okay, so I'll explain what I mean by that in a second. Now basically, what these are, if I just go back a second, so this material here is actually composed of an organic unit and a little node here which is actually predominantly metal-based. Okay, so I'm actually pretty proud of this. This is one I made earlier. So this is the reaction here between zinc nitrate. Okay, the zinc is in a 2+ form here. It reacts with benzene dicarboxylate, which is the BDC here. So these are carboxylate groups on the exterior here. And what you do is you form these cubic colourless crystals, which you see down the bottom here, which basically incorporate 4 zincs, 1 oxygen, and 3 of these BDC ligands. And basically what you end up with is this very, very, very highly porous material with a very high surface area. Okay, it's not a one-hit wonder. You can make lots and lots of these different types of materials. This is an example here where we have magnesium 2+ ions, so they're the blue spheres here. The grey here is carbon and the red is oxygen. Basically what happens is, remember that I mentioned earlier carbon dioxide is a linear molecule. The carbon is a little bit positive relative to the oxygen ends, and in fact there's an electrostatic interaction between the oxygen and the positively charged magnesium centre. So you can see that you can do a lot with these materials. You can really fine-tune them. Just another quick example. Here's an example of a copper-based material with this particular organic link. I guess I'm very proud of this because it's one I made as well. But basically you can see that these things have 3-dimensional shape and pore sizes anywhere up to sort of 20 nanometres or so. Or 2 nanometres, I should say, in that case. All right, so basically we can use any metal virtually across the periodic table, including the lanthanides. And I guess what's really neat here is that not only can we change the metal, but we can change the linker as well at will. So we can use chemistry to make different types of linking units. As well as that, we can build in selectivity. So remember I said we can do chemical reactions in these materials, and what we can actually do is incorporate functional groups like amines. So remember that the nitrogen here reacts very selectively with carbon dioxide. So we can sort of build in selectivity to these materials as well using chemistry. Okay, so just to sort of show you what us chemists really look at in terms of how would we identify a good material for CO2 capture? Well, it has to separate CO2 very selectively over nitrogen, because remember CO2 and nitrogen are the 2 major components of the flue gas. And I guess in this particular case, if we just look at this grafted material, so this with the amine on it, you'll see that in fact it takes up a lot more CO2 than it does nitrogen. So here we're looking at the amount of carbon dioxide adsorbed as a function of pressure, okay, so going up to 1 atmosphere. So in other words, this is sort of how we identify materials that are very good for CO2 capture. Okay, as well as that, you could think about adding in some more amine groups, but you get to a point where you would end up clogging the pore. So there's a really fine line here between enough selectivity and too little diffusion of gases through the pores. Okay, so that's an important concept for physisorption materials. I just want to bring this example up. This is a ZIF. And the reason I wanted to bring it up is because it's sort of like a synthetic equivalent of a zeolite. Okay, so rather than, I guess you'd be familiar with the silicon-oxygen or silicon-oxygen aluminum bonds in zeolites, in these ZIFs, we basically have a very similar coordination, but rather than an oxygen, we have what's called an imidazolate. So we can form this huge array of synthetic zeolites using transition metals, so zinc, cobalt, iridium. So I guess it's not a one-hit wonder. We can use all of the metals across the entire periodic table. Okay, so coming back to, I guess the question was asked earlier, can you do this with more than just black coal? Well, absolutely. So natural gas sweetening, so this is basically the removal of carbon dioxide from natural gas, is another extremely important application for CO2 capture. In fact, I guess this isn't such a great diagram, but if you look at the blue blobs here, these are basically Australia's major natural gas deposits, and this is really the energy of the future. Okay, so natural gas actually has a huge amount of CO2 as well. It's predominantly CO2, nitrogen, and methane. So basically, you've got to do a separation here from a different type of mix to what we've just talked about in post-combustion capture, because you've got methane thrown into the mix here. I should mention that, in fact, in natural gas fields across other countries like India, the CO2 content can actually be as high as 70%. Okay, and just remember that these are really the economies that are growing dramatically in the future. So you can see that CO2 capture is just as important for natural gas sweetening as it is for the post-combustion capture from power plants. So there's lots of applications here. So basically in natural gas sweetening, we have to do a separation of carbon dioxide from natural gas, which is methane. Okay, now there's a number of different parts to this process, and we've talked about post-combustion capture. And I guess here, yes, there are a lot of parts to the process. The most important one here is this CO2 removal. Okay, now it's very different to post-combustion capture for natural gas sweetening because the pressures are much, much higher. So here we're talking 50 to 60 atmospheres compared with 1 atmosphere for post-combustion capture. So the materials have to be very different. Okay, there's different materials requirements. And what is really being looked at here is a process called pre-combustion capture. So basically, the idea is you separate the carbon dioxide before the combustion process takes place. And I guess this is sort of how I find it easiest to understand the idea behind pre-combustion capture. So we've talked about post-combustion capture. You separate your CO2 after the combustion process. In pre-combustion capture, what you actually do is you make a syngas first up. So syngas is just a mixture containing carbon dioxide, hydrogen, and carbon monoxide. After you've done that, you do your CO2 separation. So remember, it's at very high pressure, about 50 to 60 atmospheres. And only after that, you do your combustion. Okay, so it's a slightly different process. You're separating your carbon dioxide before you actually do combustion. Now, as I said, the materials requirements here are very different. And this is basically why. So remember, with post-combustion capture, we're predominantly doing a carbon dioxide separation, which is about 15 to 16% in that mixture, from nitrogen. But in pre-combustion capture, we're predominantly doing a carbon dioxide separation, which is about 35% of that mixture, from hydrogen. Okay, so you can see then that the types of materials we need are actually quite different. Remember, the gases are different sizes as well. Okay, so just keep that in mind. All right, so just like for post-combustion capture, there's a lot of options for materials here. MOPs have actually been right at the forefront of physisorption materials, as well as that membranes. And here we can actually spin the membranes. So you could think of a big flat membrane material being spun many, many times over, and that actually functions as a very, very high surface area membrane. So there's lots of options here. Okay, now there's one more that I need to talk about, and the reason is that there's actually a power plant in Queensland running under Oxyfuel combustion. It's only in the demonstration phase, but basically what you do here is you separate air, and this is actually a costly process. This uses cryogenics, so there's a big need for new materials for air separation as well. And then what you do is, after you've separated your air, you basically do your combustion in almost pure oxygen. And if you do that, then what you get out is almost pure CO2. And you use a little bit of that to mix in here just to keep the temperature down a little bit. So this is basically what's being touted as a zero emissions power generation. These plants are very costly. They can't be retrofitted. You have to build a plant from the ground up. But you can see that there's lots of options here for the future. Okay, so what do we do with the CO2 once we've captured it? Well, bless you. All right, so you've captured your CO2. You've used a particular material or a solvent to separate it. What you have to do then is you have to transport the CO2. So, of course, you've got a very, very high volume of flue gas, and, of course, that's really not feasible. So what you have to do is somehow compress the CO2 into a much smaller volume, then somehow transport it and store it somewhere. Okay? So here comes back to some physical chemistry. this is actually the phase diagram for carbon dioxide, and I guess the two important points here are the triple point, which is the point where the solid, liquid and gas all coexist, and the critical point here where above which you've got a supercritical carbon dioxide fluid. So really, if you take a look at the volume that is occupied by carbon dioxide, then you can see as a gas, it takes up a lot more space than it would as a liquid. So basically, we have to compress the CO2. In fact, throughout the United States, there are pipelines already there for natural gas transport. So there's already some existing infrastructure, but you can see that you have to think about how to actually compress it and then transport it as well. Okay, so what do you do with the CO2? All right, so here's what I think you could do with it, but Coke's not too good for us. So there's a lot of options, obviously. In fact, CO2 is the 19th most important commodity chemical across the world. You can make fertilisers from it, pharmaceuticals from it, fire extinguishers, dry ice, as we mentioned before. So there's a lot of possibilities here. The problem is that there is so much CO2 that you would saturate global markets. And this is really the problem of CO2 use as a commodity. You can use a little bit of it, but there's simply too much of it. So we have to find some other way of storing the CO2. Now, if you think about what might be the options, or the storage or sequestration options, then you can see that in oceans, in geological formations, there's actually a lot of capacity for CO2. Okay, so that's the key thing to realise. Now, I've put a question mark here. Is CO2 storage a mature technology? The reason is that, in fact, it's been used for over 50 years or so in the United States. And basically what they do here is they pump the CO2 back down into the ground, and it's used to force more oil and gas up. So it's actually a money-making exercise here. So there is some technology for CO2 storage that is absolutely commercially viable. Okay, so that's important to realise. You could also think about storing the CO2 underground. So, for example, in deep geological formations and saline formations. And I wanted to bring you to an important Australian project. This is actually the largest storage project currently going on worldwide. The Otway Basin is just down a little south of Melbourne in Victoria. And basically what they're doing here is that they're pumping out natural gas, and they're pumping it back down to see whether it can actually be stored underground. So you'll notice that up top here, there's a lot of monitoring going on. This is a major operation by the CSIRO in Australia. So they're doing a lot of monitoring to check just how stable this stored CO2 is. So this project is going to be going on for decades. What else could you do with it? Well, you can make limestone. We've already talked a little bit about this before. So you can make mineral carbonates, but then what do you do with those? I guess you could make building materials out of them. If you wanted to store them, then you would have to have a lot of space to store them. Okay, so that's something to think about there. As well as that, if you planted big forests near power plants, would that be a good way of capturing or sequestering the CO2? Remember, plants love CO2 for photosynthesis. Well, the problem is you'd need a lot of land, you'd need a lot of plants to do that, but it is one important option. It may not be cost effective, but that's still to be determined. And of course, there are some collateral benefits. So in Australia, we have a lot of problems with top soil degradation, so that may actually be one important possibility. As well as that, algae love CO2 as well. And so there's the thought of actually these big algae ponds that can actually be used for biomass fuels. And of course the algae will take up the CO2. So this is one possibility for an actually carbon negative sequestration option. Okay, now this is a very, very problematic CO2 storage option. That is pumping it down under the ocean, so to a pressure where the CO2 would actually go supercritical or liquid. I have to tell you that BP have actually completely gone away from this possibility. There are actually no places now worldwide even trying out this storage option. But I think it's important to just point out that it was on the table there for some time. You can imagine that as soon as you start pumping CO2 into the ocean, just like our carbonated beverages, the ocean will become quite acidic. So you have to think about how that would impact on the long-term welfare of the world, and I guess that's the reason why they turned away from it. There was one interesting thought for some time that you could fertilise the ocean, so you could add iron in. If you have more CO2, you need more iron to take part in the photosynthetic process, so there was some thought that you could actually fertilise the ocean. An interesting one, but I'm not sure that idea didn't last for too long. And of course, how safe is storage? It's something that I think a lot of the public are actually quite concerned with. It has to be environmentally acceptable, it has to be safe, and of course it has to be environmentally viable. And as I said before, there are a very large number of programs underway across Australia. Probably the most important here are the Hazelwood Power Station, which is a capture project that we talked a little bit about before. The Gorgon project and the Otway Basin project are two purely storage projects that are fairly well along the way. So there's some very good data already being generated from these two sites. But as well as that, you can see there's a lot of other sites around Australia that are actually moving towards trying out CO2 capture. So I guess what I wanted you to take from this is that it's not all doom and gloom. There are things happening and there are positive things happening. Whether the politicians come along with the scientists is another thing. Okay, across the world there's actually a lot happening as well. As I said, the Otway Basin project is one of the largest storage projects worldwide, but there are other major storage projects going on up here in Norway, down here in the States, and in Salar in Algeria. So you should be aware that there is a lot going on worldwide here. So the bottom line, I think, is that CO2 capture and storage is a viable option. It will be vital for the future. There aren't any fully integrated carbon capture and storage systems in Australia at the present time, but as I said, there are some discrete storage projects and some discrete capture projects already going on. The goals here are really to get the cost of capture down to about 100 to 300 US dollars per tonne. And as I said, there are both post, pre and oxyfuel combustion possibilities for capturing the CO2. There are a lot of options for sequestering the CO2 as well, whether it be in deep geological formations or using it as a commodity chemical. And I guess in terms of what we can actually do, well, yes, we should all be thinking about our energy efficiency, turning off lights when we're not in the room. But in the short to mid-term, I think it really will be carbon capture and storage that will be the key and important action plan here. In the longer term, of course, we must move to renewable energies like solar and wind and wave power. And I guess I've done a little bit of travelling over the last few years. As Chris said, I spent some time in the States in Berkeley. These are actually all my own photographs of some places I've been around the world. This was actually taken out of the Sydney Morning Herald, but I guess I know there's a lot of conjecture about whether climate change and global warming is actually true, and I can just say that in looking out my bedroom window, I don't think this is right. All I can say is that global warming does appear to be true, and I think carbon capture and storage is definitely one viable option for the future. And I'll just leave you with that thought. And thank you very much for your attention, and I'll be very happy to answer questions.